start the first presentation by young researchers of this ALGA. So this is a series of short lectures that are given by either PhD students or young postdocs and young researchers. So our first young researcher of today's session is Ageu Freire from UFRJ, and he will speak on a splitting criterion for uniform vector bundles. Please, Ageu.
Thank you. So let me just stress here, this is a work in progress with Carolina Araujo and Lucas das Dores. And I will start with vector bundles on the projective line. So vector bundles on the projective line are all classified, and this is a classical result due to Birkhoff-Grothendieck. And it says that for a vector bundle, every vector bundle on the projective line, it splits as a direct sum of line bundles. What it means that there exists A1 up to AR integers such that we have these isomorphisms. For curves of higher genus, it does not hold. And this is important to study vector bundles for more general varieties, like the projective space Pn. How we do it? We can restrict the vector bundles, vector bundles on Pn, to each line, and understand how the restrictions varies when we vary the line. And when the restriction of a vector bundle to a line does not depend on the line, we say that the vector bundle is uniform. Again, by the Grothendieck theorem, it means that there exists A1 up to AR integers such that the restriction for the vector bundle to a line is isomorphisms to this direct sum of line bundles. And a problem is that if you take an uniform vector bundle, we want to know when this uniform vector bundle splits as a direct sum of line bundles. And here I have two results. The first one, due to Van de Ven, says that if we have a vector bundle that the restriction to a line is trivial, actually this vector bundle is trivial. And the second one, for a uniform vector bundle on the projective space, if the rank of E is greater than 2 and is smaller than n, this vector bundle splits as a direct sum of line bundles. And now we would like to extend the notion of uniformity for more general variety. For this, let's consider X a projective variety over a field that is algebraically closed and have characteristic 0, and consider E a locally free sheaf on X. Okay, and again, and also denote by red curves the family of curves, rational curves that is contained in X, on X. And now we can define this notion of uniformity, but for this we have to consider an irreducible component of red curves on X, and says that, and we can say that this locally free sheaf on X is H uniform if when we take two lines or two rational curves on H, the restriction is isomorphic. Again, by the Grothendieck theorem, it means that there exists A1 up to AM such that the restriction to a rational curve on in H is isomorphic to this direct sum. And here we can assume that A1 is greater than A2 and so on. Okay? And the same problem can be asked here. Given an H-uniform locally free sheaf, how can we say that this H-uniform locally free sheaf splits as a direct sum of line bundles? In order to answer this question, or at least a part of this question, let me fix some notation. With given H an irreducible component of right curves and a small x in our variety x, we denote by H subindex x the normalization of the family of curves in H that pass through x. And by a k minus 1 tuple d2 up to the k, we denote, and also E a locally free sheaf, we denote by F subindex and E the flag scheme which parameterizes sequence of locally free quotients of E, where each part here in the sequence of quotient we are assuming to have rank di. Now, assuming x as before, and taking E an H uniform locally free sheaf on X, we have from the Grothendieck's theorem that the splitting type of E, which means that the restriction of E to any line, is isomorphic to this direct sum. And as before, we assume here that A1 is greater than A2, and so on. Now, we would like to construct a map which will bring to us some properties of the splitness of a locally free sheaf. For this, we consider X, a point in big X, and a line passing through X. By the splitting type here, we have a natural sequence of locally free quotient like this. Since we are assuming A1 is greater than the other, we have the first natural quotient here. This is when we forget this part here. This is true just because A1 is greater than the other. Again, we are assuming A2 greater than A3 and the other ones. Then we have a natural quotient when we consider the sum started on OP1, A3 up to R3. And doing it, we have the last quotient here when we consider just the last part of the sum on here. And again, this is this quotient that exists because AM is smaller than the others. Now, since this is a sequence of locally free quotient, we can take the fibers of X. Remember X, we fixed it before, take this sequence of locally free quotients. And now when we take the fibers over X, we have a sequence of quotient on the fiber X. This is the fiber of the locally free sheaf E. Here, each part of this quotient, we are assuming having to, they have rank di, where di is equal to the sum of Rj, where Rj appear here, with j going to, where j goes to I up to m. And using this association, which is for any line, we can associate this sequence of quotient, we have a map. A map which takes a line passing through X and associate this sequence of quotient. And we say that this map is the flag map. For example, if just me give a simple example, if we have the projective space Pn and the tangent bundle of Pn, it's well known that the restriction of any line of Pn is isomorphic to O2 plus O1 up to n minus 1. Again, for P a point in Pn, it's also well known that the variety parameterized lines passing through P is isomorphic to Pn minus 1. In this case, this flag map is the map which goes to Pn minus 1, which is the variety parameterized line passing through P, and arrive in the flag which takes, here we have one, which have a flag which gives a point inside a space of dimension n. This is isomorphic to Pn minus 1, and this map just take V and goes to V. This is the identity map. And as I told you, this map brings us some condition of splitness of locally free sheaf. It states in this theorem, together with Carolina Araujo and Lucas das Dores, we input some conditions on the variety, and we proved that E splits as a direct sum of line bundles if and only if the flag map we defined before is constant forever x in x. If we impose the condition that hx, the dimension of hx does not depends on the x, small x in x, we can state using the rigidity lemma that actually E splits if and only if the flag map is constant for one point in big X. And we use it to apply in two cases. The first one for the Grassmannian. If you have a locally free sheaf of rank R and assume that K is greater or equal than 4 and R is smaller than this number here, then this locally free sheaf splits. I have a table with the more simple case. And we also apply for a non-homogeneous variety. This is the odd symplectic Grassmannian. Again, if you have a locally free sheaf of rank R, and we have the rank is smaller than the minimum between these two numbers, this locally free sheaf splits as a direct sum of line bundles. Thanks.